Hello everyone, welcome back to my VLSI diary. My name is Shivangi Upadhyay and today we are starting one of the most important topic in digital electronics and RTL design, which is flip-flops. If you want to understand sequential circuits, finite state machines, registers, counters, memory blocks or any RTL based digital design, this is where it all begins. Until now, we may have studied combinational circuits where output depend only on present inputs. But today, we enter the world of memory, and the smallest building block that can remember a value, that's the flip-flop. Now, let's understand what a flip-flop actually is. A flip-flop is a sequential logic circuit that can store exactly one bit of data, either 0 or 1. Unlike combinational circuits, flip-flops depends on present inputs, previous output, and most importantly, a clock signal. You can think of a flip-flop as a tiny memory cell controlled by a clock. It changes state only at a specific clock edge, either rising edge or falling edge, which makes digital systems synchronized and stable. So, if combinational logic is the brain, flip-flops are the memory of the system. So, let's talk about this super small but extremely powerful in digital electronics flip-flops. You might think it's just one bit. How important can that be? But trust me, almost every digital system depends on flip-flops. Let's understand why. First of all, flip-flops stores just one bit, but that's huge. A flip-flop stores exactly one bit like either 0 or 1. Sounds tiny, right? But imagine millions of flip-flops connected together. That's how memory, processors, registers, and complex systems are built. Even your CPU is basically a massive collection of flip-flops working together. Second, they make sequential circuit possible. There are two types of circuits like combinational circuit which depends only on current inputs and sequential circuits which depends on past outputs. Now, here's the key. Flip-flops stores the past state. Without flip-flop, we could only build combinational logic, like no memory, no history, no state, no smart behavior. Third, they built registers, counters, and pipelines. Let's break it down. A register is just multiple flip-flops storing multi-bit data. And a counter is flip-flops changing state with every clock cycle. Processor pipelining use flip-flops to store intermediate stage result. Basically, if you are building any serious digital system, flip-flops are involved. Fourth, they are the heart of the FSMs, finite state machines, which we use everywhere in RTL design, stores the current state using flip-flops. On every clock cycle, current state, then next state. Without flip-flops, no state machine retention, no FSM, no control logic. Fifth, they synchronize everything with the clock. Flip-flops works with the clock edges, rising or falling. They ensure data is captured at the correct time, glitches are avoided, signals are synchronized. That's why in hardware design, timing is everything, and flip-flops control the timing. Sixth, in RTL, every always at the rate posage clock means flip-flop. If you are writing Verilog or system Verilog like always at the rate pauses clock, congratulations, you just described a flip-flop in hardware. The synthesis tool doesn't see the code. It sees hardware and that hardware is flip-flop. Flip-flops may store just one bit, but they are the reason that memory exists, FSM work, processor function, and digital systems remember everything anything at all. Without flip-flops, digital electronics would just be instant logic with no memory. And memory is what makes the system intelligent. Alright, let's quickly understand the different types of flip-flop, the building blocks of digital electronics. First, SR flip-flop, set reset. Simple memory element, but watch out. When S and R both become 0, boom, invalid state. Next, D flip-flop, the most popular one. It stores the value of D exactly at the clock edge. Clean, simple, no invalid states. That's why engineers love it. Now, JK flip-flop. It's like the upgraded version of SR, and when J and K both are 1, it toggles. Super useful. Then comes the T flip-flop. Toggle mode on. It changes output on every clock pulse. Perfect for counters and frequency dividers. And finally, edge triggered flip-flops. They react only at the clock edge, either positive edge or negative edge. Precision time matters. Now, let's talk about the most basic memory element in digital electronics, which is SR flip-flop. SR stands for set and reset. It has two inputs, S and R, and one output Q. When S equals to 1 and R equals to 0, the flip-flop goes into the set state, which means Q becomes 0. And when S equals to 0 and R equals to 1, it goes into the reset state, so Q becomes 0. If both inputs are 0, the flip-flop simply holds its previous value. It remembers the last state. That's why it's called a memory element. But here's the catch. When both S and R are 1, it enters a invalid or forbidden state. And because of this limitation, SR flip-flops are rarely used in complex modern designs. Still, it's super important because it helps us understand how memory works at most fundamental level. Now, let's talk about the most important flip-flop in digital design, the D flip-flop. D stands for the data or delay. And trust me, this is the most commonly used flip-flop in digital and VLSI systems. It stores just one bit of data but updates the output only on the active clock edge. That means it gives stable and predictable data storage. No confusion, no invalid state. And here's the golden rule. On every positive clock edge, Q equals to D. Whatever is at D gets stored in Q. Now let's quickly see the signal. D is the data input. Clock controls when the data is captured. Q is the output and Q bar is the complement if needed. Simple, clean and powerful. Because of this simplicity, D flip-flops forms the building block of registers and memory elements. They are everywhere inside processors, in pipeline stage of RTL design, shift registers, counters and timers, finite state machines, and memory blocks in FPGA and ASIC designs. In fact, almost every sequential circuit internally uses D flip-flop. But yes, nothing is perfect. It stores only one bit per flip-flop. It needs proper clocking. Glitches can cause issues. If setup and hold time are violated, metastability can occur, and it cannot toggle or reset by itself without extra logic still. If digital systems had a heart, it would be the T flip-flop because every synchronous design depends on it. Now, let's level up from SR and meet the smarter version, that the JK flip-flop. JK is basically an improved version of SR flip-flop. The biggest upgrade, it removes the invalid state that SR had when both inputs were 1. Here is how it works. J is the set input and K is the reset input, and the clock decides when the state changes. On the active clock edge, if J equals to 0 and K equals to 0, no change. If J equals to 0 and K equals to 1, reset. If J equals to 1 and K equals to 0, set. But here's the powerful part. If J equals to 1 and K equals to 1, it toggles. Yes, the output flips from 0 to 1 or 1 to 0. That's what makes JK predictable and powerful. Because of this toggle feature, JK flip-flops are widely used in counters, frequency dividers, and control circuits. But from the modern RTL perspective, they are more complex than D flip-flop and rarely used directly in FPGA or ASIC designs. In fact, most designs prefer D flip-flop for simplicity and clarity. Now, for the circuit explanation, let's quickly understand the hardware behind it. This is the clocked JK flip-flop built using NAND gates. On the left side, we have an input getting NAND gates. They take JK, the clock, and the feedback from output. The feedback from Q and Q bar is secret sauce. It enables the toggle operation when J and K both are 1. On the right side, we have two cross-coupled NAND gates. This forms the memory latch. Top output is Q, bottom is Q bar. When the clock is high, the circuit responds. When it's low, it holds the previous state. But here's the important VLSI insight. This is a level triggered JK flip-flop. If J equals to K equals to 1 and the clock stays at high too long, it can cause a race around condition. And that's exactly where modern hardware prefer edge trigger D flip-flops. So remember, J and K flip-flop is powerful conceptually, but D flip-flop rules in real-world RTL design. Now, let's move to the T flip-flop, also known as the toggle flip-flop. T stands for toggle, and the name says it all. When T equals to 1, the output toggles its state on every active clock edge. That means if Q was 0, it becomes 1. If it was 1, it becomes 0. But then T equals to 0. No change. The output simply hold its value. Fun fact, a T flip-flop can actually be derived from a JK flip-flop by setting J and K equals to T. Now let's talk about the inputs. We have the T input, which controls toggling, the clock, which decides when the changes happens, and optionally reset or preset in practical designs. Operation is super simple. If T is 0, it shows holds. If T is 1, it shows toggle on every clock edge. Because of this behavior, it stores a 1-bit state and is perfect for counting operations. That's why T flip-flops are widely used in frequency dividers like divide by 2, 4, 8, and so on, binary counters, clock division circuits, toggle switches, and control logics in FSMs. But yes, there are limitations. You cannot directly load arbitrary data. It's not suitable for general data storage like a D flip-flop, and it's less than flexible compared to D and JK flip-flops. That's why in modern RTL design, we usually don't use T flip-flop directly. We derive from behavior. In fact, in RTL, a T flip-flop is commonly implemented using a D flip-flop with D equals to T XOR Q. And that's powerful. So here's the takeaway. T flip-flops are simple and extremely useful for counting and clock division, but not ideal for general data storage. Now, let's move to something really important in flip-flop evolution, the master-slave flip-flop. So, what exactly is it? A master-slave flip-flop is built using two latches connected in series, one called the master and other called the slave. And here is the interesting part. When the clock is high, the master is active. It captures the input data at the same time the slave is disabled. Then, when the clock goes low, the master stops updating and the slave becomes active, transferring the stored value to the output. So, input sampling and output updating never happen at the same time, and that's the key idea. This clever arrangement eliminates the race around condition that we saw in level triggered JK flip flop. Even though it's built using level sensitive latches, it behaves like an edge triggered flip flop. Now let's quickly look at the inputs. The data inputs, which could be D, JK, or T, depending on the implementation. The clock, which alternate control between master and slave, and optionally reset or clear for initialization. Here is the working principle in one line, like clock high, then master active, clock low, then slave active. Output updates only once per clock cycle, and because of that, it ensures stable and predictable operation. Applications. It was widely used to eliminate race condition in JK flip-flops. It formed the foundation for early synchronous digital systems. It became the stepping stone towards modern edge trigger design, and it is still very important for understanding timing behavior in sequential circuits. But yes, there are trade-offs. It requires two latches, so more hardware, that means larger area, higher power consumption, and slightly slower performance compared to modern edge trigger D flip-flop. That's why in today's ASIC and FPGA design, we usually use optimized D flip-flop instead. But conceptually, master slave flip-flops were a major milestone. So here's the takeaway. Master slave flip-flops solved race conditions by separating inputs, sampling, and output updating, and paved the way for modern edge trigger designs. Now, let's talk about something absolutely critical in digital design, the timing diagram. So, what is timing diagram? It's simply a graphical representation of signal versus time. It shows how the clock input and output changes over time. And if you are working with flip-flops, registers, or FSMs, timing diagrams are not optional, they are essential because sequential circuits are all about when things happen, not just what happens. Now, why do timing diagrams matter so much? They help us to visualize exactly when data is sampled and exactly when the output changes. They are heavily used in simulations, waveform analysis, and RTL verification. If there is a timing bug in your design, the waveform will expose it. Let's quickly look at the key signal you will see in a timing diagram. First, the clock. This synchronizes everything. Then the data input. It could be D, JK, or T, depending on the flip flop. Then the output Q, that's the stored value. And sometime you will see a reset or enable signal controlling operations. Now, here comes the most important part. Timing parameters. Setup time, which is the data must be stable before the active clock edge. Then hold time, which is the data must remain stable after the clock edge. Clock period, the time between two clock edges. And propagation delay, the time it takes for the output to update after the clock triggers. If setup and hold time is violated, we get timing violations and that can be cause metastability, which means unpredictable output, and in real silicon that's the dangerous thing. Now, how does this connect to flip-flop? Simple. The output queue changes only at the active clock edge. The input is sampled exactly at that edge. And timing diagram clearly shows this behavior for D, JK and T and even master slave flip-flops. So, timing diagrams allow us to see when signal changes, and that makes them absolutely essential for designing reliable and correct sequential circuits. Flip-flops in RTL coding. In RTL design, flip-flops are inferred using clocked always blocks. Every storage element in RTL corresponds to a hardware flip-flop. Flip-flops defines state, timing, and data synchronization in digital systems. How flip-flops are described in RTL. Triggered on clock edge, pauses, and negage. Use non-blocking assignments, typically written using always at the rate pauses block. This directly maps to a D-type flip-flop in hardware. Basic D flip-flop RTL example is given below. So, the key RTL coding rules for flip-flops are use non-blocking assignments, prefer synchronous reset for ASIC designs, avoid mixing blocking and non-blocking in sequential logic, avoid incomplete if condition because with it can infer latches. What RTL tools infer? Always at the rest pauses clock for D flip-flop, reset inside block, flip-flop with reset, multiple flip-flops, which is registers, and combined with logic, data path, and FSM storage. Why flip-flops matter in RTL? Stores data across clock cycle, enable pipeline counter register FSMs, critical for timing closure and synchronization, foundation for processors, controllers, and interfaces. In RTL design, flip-flops are the heart of the timing and storage. Every always at the rate pauses clock you write is a real hardware flip-flop waiting to be synthesized. Alright, now let's talk about where flip-flops are actually used. Because trust me, they are everywhere in digital systems. First, data storage. A flip-flop stores just one bit, either 0 or 1, but combine millions of them and you build a memory. They are the basic building blocks of registers and memory units. Now, moving to registers. A register is simply a group of flip-flops working together. 8-bit, 16-bit, 32-bit. It's just multiple 1-bit flip-flop combined. Now, that's how CPU and microcontrollers store and move data internally. Next, counters. Using T or JK flip-flop, we can design synchronous and asynchronous counters. These are used in timers, digital clocks, and even frequency division circuits. Now, let's talk about shift registers. Using D flip-flops, we can shift data left or right. This is super important in serial to parallel and parallel to serial communication. That's how communication systems move data efficiently. Another power application is frequency division. A simple toggle flip-flop can divide a clock by 2 and more stages, and you get divide by 4, divide by 8, and so on. Now comes one of the most important application, finite state machine. Flip-flops stores the current state of the system. Control units, traffic light systems, communication protocols, all of them rely on flip-flops. Then we have debouncing circuits. Mechanical switches don't produce clean signals, so flip-flops help remove unwanted fluctuations. And finally, synchronizers. In clock domain crossing, signals can become unstable. Flip-flops are used to prevent metastability and ensure safe data transfer between clock domains. So, here's the big picture. Flip-flops are not just theory. They power register, counters, processors, memory, communication systems, almost everything in digital electronics. If you understand flip-flops, you understand the foundation of modern digital systems. And that brings us to the heart of sequential digital design, flip-flop. Flip-flops are the fundamental building block of sequential circuits. Unlike combinational logic, they stores memory, and that memory is what makes time-dependent digital systems possible. Throughout this presentation, we explored the complete journey from SR, JK, D, and T flip-flops to master-slave configuration and edge-triggered behavior to timing diagrams, setup time, hold time, and clock transition. And finally, real-world application like registers, counters, FSMs, and clock division. But this is not just a theory. Understanding flip-flop is critical if you want to design reliable synchronous systems, avoid timing violation and metastability, write efficient RTL code, and build robust FPGA and ASIC architecture. Every processor, every embedded system, every VLSI chip, at the core you will find the flip-flop. They are the storage element that ensures predictable, stable, and synchronized operation in modern digital system. So, if you truly understand flip-flops, you understand the foundation of digital design. You can design reliable synchronous systems, you can avoid timing violations and metastability, you can write efficient RTL, and you can build real FPGA and ASIC architecture. And if you are serious about growing in VLSI and RTL development, don't forget to like, subscribe, and hit the bell icon so you never miss an upcoming lessons. And with that, let's continue this journey, turning concept into RTL and RTL into real silicon. I'll see you in the next video. Thank you.